Welcome to our serverless.NET patterns presentation. Today I'm going to talk about how to write your Lambda code in a way that makes it easier to test. And hopefully that's a pattern you can use for your project as well. As always, this will be available on YouTube afterwards. And then also the code I'm presenting today is all on GitHub, and I'll provide the links at the end. So I have a simple CRUD application or service to showcase kind of like, the basic setup of a Lambda function. Well, it's not super basic because we're going to have some IO, we're going to have some store operations. It covers kind of a little bit the spectrum, but just have a foundation about, something that's operational, makes it a little bit more interesting for testing. Then I wanted to revisit a couple of functional programming concepts, I think, which are relevant when we think about testing. And what are the important aspects that we need to keep in mind, and how we make keep our sanity a little bit more easily. Introduce the dependency provider pattern, which is something we've been using at MindTouch and now at NICE for decomposing business logic from other aspects of it so that it becomes testable, so that it's easier to validate that it's implemented properly and that it has all the properties that we want it to have. And then I'll go back to effectively the same service, but this time augmented with a dependency provider pattern, show how that has changed from the previous version, how the code has been refactored, walk through, and then also show how the tests are organized. So this should give you a fully good idea of kind of like a starting point of, a somewhat trivial Lambda-based service with some real interactions on how that may look like when you just make it work, how you then refactor it into something that is easier to test, and some of those concepts you should keep in mind. And then, we'll have a wrap up at the end. So let's get started with the sample application. So like I said, it's CRUD, so create, read, update, and delete. Although I guess in this example, there is no delete. And there are 4 endpoints. I used API gateway, but the mechanisms discussed today would apply to SQS queues, kinesis streams. I mean, they work for anything, right? I mean, the Lambda reacts to some kind of event, does its work, and interacts with other services. And Lambda is actually quite unique in that regard because it's entirely ephemeral, which means that by very definition, you cannot keep things in memory indefinitely, and you cannot keep things in local storage indefinitely because they will just go away. So Lambda has to interact with the outside world, and that's a really important property. The 4 operations are, one is a simple, so it's kind of like a little blogging kind of API I put in. It's a toy API, but hopefully illustrative enough for our purposes. There's a post preview endpoint, which kind of allows pre-render markdown into HTML, so you can like preview it without actually storing it. Ability of creating a new post, ability of getting all the posts that have been created, and then ability of viewing a post rendered in HTML. So again, fairly basic functionality, but even then, where we have a few interesting interactions which allow us to apply the dependency provider pattern, as we will see later. So what I would like to do now is jump into the code. So like I said, this code is on GitHub, and I'll provide the link at the end. And I organized it into 2 subfolders, example 1 and example 2. Example 1 is written without the dependency pattern applied. It's a bit bigger. And example 2 is with. So we're going to start with example 1, and they share a lot in common, but this will make it easier to kind of like highlight the changes that happen between the 2 approaches. So we have in example 1, we have the module definition, which will create our CloudFormation stack. And so this is a fairly simple module. It contains a Lambda function that defines the 4 API endpoints that are interacted with. And then it also has a resource, which is an DynamoDB table that we have read-write access to, that is scoped to the function. And it has the setup of this DynamoDB table is virtually identical. It's a little simpler than the one from the last DynamoDB talk. But we just define our partition key and our sort key as hash and range, which is kind of like what I recommend you always do I did remove the TTL just because we don't need it for today. But again, I think in general, you probably want to have that defined in on that DynamoDB tables. So that's the entire module. So it's very short. There's then a .NET project, which is the API function. And that's really just a single file. So it's a very, very simple implementation. And in here, we do two things. When we initialize, we basically read the name of the data table so we can connect to it. We initialize this data access client. I'll talk about that a little bit. Again, we covered kind of this pattern in the DynamoDB presentation from last time. It's kind of, how you keep your sanity a little bit better by using DynamoDB and taking advantage of it. But ultimately, data access client is just a client we have written for accessing the table with some predefined operations, access patterns. And then we have our endpoints as defined by our module file. So if I bring that back up, you can see here, this endpoint will invoke our preview post method, post, create post, list post, and view post. So these correspond to the ones in our file. And frankly, the most interesting part kind of like of the business logic we're going to be working with today are really being provided by this markdown library called markdig. So I have it at the top right here. And so this one allows us to convert markdown into HTML, has a whole bunch of configuration options, none of which I'm taking advantage of today. I just wanted to kind of like show the interactions between systems. So our preview method just takes the request. From the requests, it extracts the markdown property where the markdown is, and then calls the toHTML static method on the markdown class to convert it, and we just send that back. So if you look at our preview post request and preview post response class definitions, they're incredibly simple. We simply we defined that the markdown field is required. So again, if you send something in and it doesn't have the prerequisite field, it gets rejected by API gateway. And then we have a response that is predefined that would simply populate and return back. So that's done here. And we look at the rest of the functions, and it's pretty much equally trivial. Right? So create post, again, with a post request that has the markdown, and then have a response that gives it back the ID. And so we need to create then a post record. This is what gets stored in the DynamoDB table. We give it a new ID, which is based on a GUID. We set the date time field to the time it is now when it was being created. And we initialize a property markdown to simply be the one that we got from our request. So you can see there's no validation going on of any kind. Again, it's a toy application, but good enough for what we want to cover today. And then we call our data access client, which is responsible for taking this data structure and storing it in DynamoDB. It comes back with a Boolean if it was successful or not in doing it. If it isn't, we log a failure and initially created to false. And so if there was any reason that it wasn't created, we come back with a 500 error body that says unable to create and just set the content type. So this is just basically the method saying, hey, I wasn't able to complete and give you back the expected data type. So we throw an abort exception, which allows us to give back a different kind of payload. And once we get to this point, well, we know that we need to initialize the ID of the created post. That comes from the record we created earlier here. And so that gets returned. And the rest of the code is even simpler. Create was by far the most complicated one. View simply calls get post record, pass in the post ID. If we don't find a record, we abort with a not found exception. Otherwise, we initialize a view post response. Again, set all the fields. And since we limited right now to .NET Core 3.1 or C#9, I guess. No, C#8. We can set these to init, so you just have to remember that to set them explicitly yourself. So that will be nice in the next once .NET 5, .NET 6 are supported in Lambda. And then lastly, we have this list things, which allows us to list all the records that exist. So let's just quickly invoke it just to see how it works. It's very simple. So initialize Postman here. Great tool for testing your API manually. So create post. As I said before, we have our endpoint. Simply as a post operation on /posts. And then we and in a payload. And depending if it's cold start, and we get back the ID. And so now if I go to list posts and I send the request, and I set it up, I deployed a little bit earlier just so that we wouldn't have the delay from initializing it. And you can see now there are two ones. The second one should be the newer one, right? Yep, okay. So tested it. No. I don't think they come back specifically sorted in any order. I don't think I put a sort on the time. So that would be a validation test to make how the collection is returning it. And then I can say, oops, where say create post, it came back with this ID. And then I can say view posts. So I go to the posts endpoint, the ID, send that. And then so we get back the ID, the timestamp when it was created, and the rendered HTML. So it's, again, very, very simple service. Some of the things I skipped over is the data access client. I don't want to spend too much time on it, but this whole subfolder contains effectively a definition for a class that allows to interact with DynamoDB that uses the Lambda shard DynamoDB native library that makes things a lot easier to interact with DynamoDB. As you can see, the operations are relatively straightforward. Put item, you give it the condition that you don't want it to exist. So you don't want to overwrite the one, you want to make sure it's a create operation, and they execute it. There's a data model, which has to do with how things are mapped into DynamoDB. We use for the partition key a constant, again, not recommended for large setups, but for our type application, perfectly fine. And then our sort key is the ID so that we can do a query on it. And we can take a quick look at that in the deployed stack. So if we go to resources here and go down to data table and open it, view items. So we can see here the items. So I don't know, okay, that was the one I created earlier. So the second one is the new one, right, with high. So that's the markdown, the date time, the ID, and then the library also stores what was the .NET type that was used for serializing. So we can deserialize it accordingly. So that's all in the data access thing. Frankly, that is just to make it easy to work with DynamoDB. So not super relevant today, but just so you know what's behind it. All they do is basically take this post record model. Oops, oh, I'm in the wrong folder. Data access, the records, here we go. This is what we marshal in and out of DynamoDB, right? That's a row in DynamoDB. We only have one type in DynamoDB. This is not one where we project multiple types simultaneously. It's a single table design. So really, really simple. Cool. So you can see from the implementation, it's just 100 lines of code. This is a very, very small Lambda function. It does everything pretty much straight up with the exception of the data access client, which helps a little bit with the marshaling. So we don't deal directly here with that aspect in complexity. But that aside, we're talking about a pretty primitive implementation. And again, probably the most interesting part is actually completely outside this code in its library, which is the conversion to HTML. Not that particularly important. Now, I chose these particular access points for a reason. And that's kind of like where we're going next. No, present. Can I just say present for me? Yeah, okay. I want to start at the beginning. Loading. Okay, here we go. So I think this one is kind of obvious. When we're done the testing, we want to make sure that our implementation is correct, that it behaves the way we want it to behave. That seems kind of like the basic idea behind testing. But we probably also want it to perform fast. So we can run it fairly quickly and get this validation. But if it takes a lot of effort, then that's less likely to happen. And then also we'd like it to be done in a way, organized in a way that it makes it easier for us to achieve good coverage. And that, depending on how you organize your tests, there can be some complications around it. So we'll cover some of that as we start talking about testing. I should probably move this slide a little bit later, because the interesting thing I want to talk about right now is the type of functionality we need to test. And this is where it makes sense to just remind ourselves of some of the basic concepts of functional programming. Functions, general, like methods and so on, I mean, they have an entry point, right? That's the method that you call. You pass it parameters, and then something comes back, either through a return value or through an exception. Those are kind of like the two exits that you can have. Now, return values can be returned different parts of the method. So there can be multiple exit locations inside the method, but ultimately it's pretty well defined. If you can predict every exit value by only looking at the entry values, so the parameters, the method and the parameters, then your method is stateless. For example, in our previous code, our preview method, that one took markdown in, rendered it, and sent it back. It didn't interact with anything else. So that is a stateless endpoint. But only by knowing what we're sending to the endpoint, we should be able to always predict what we're going to get back from it. There are no dependencies. So that's the simplest kind. That's a pure function in functional programming. The next kind are stateful methods. So these are where the outcome, what you get back from the invocation, not only depends on what you supplied, but also something that gets taken from somewhere out of band. So you don't see it as part of your interaction, but it can have an impact on what happens. That's a stateful method. For example, the read operation where we asked for a blog post to be rendered. Well, we passed in an ID and we got back HTML that was stored previously. And we could only do that by reading the data from somewhere else. So that endpoint is stateful. Again, by virtue of being stateful, when we have the entry and if we can observe what is being read, we can again predict everything that happens. And then there's finally a last kind that we need to be mindful of, and that is stateful with side effects. So for example, create post falls in that family. We are not only dependent on what we supply, what it might be read from somewhere else, but we also have an impact on the world at large. Either that impacts next invocations of our logic or invocations of somebody else's logic if it's a shared data source. So those are the three types of functionality that really exist when you think about functions and being able to predict what the outcome of one is. And so when we talk about dependency providers, really what we're talking about is to make those read-write operations just as present and visible as we do with our parameter declarations and our methods. So we're really making sure that anything that our business logic reads from, be it the parameters or another store, we can control. It is explicitly defined as an interface that our business logic needs and that supplies the information it is requesting. Similarly, if our business logic has an impact on code somewhere else, on data somewhere else, we have, again, in our dependency provider, established those methods that can be invoked to store a record, create a record, delete a record, whatever the operation might be that has a side effect. But fundamentally, the combination of parameters and the dependencies have to give us full predictability on what the outcome is that we expect. So given these parameters, given the state of the world, I expect this outcome and this side effect. So now we have complete visibility and we can start achieving the objective we had before by able to write unit tests that actually achieve this. So the way our code then is organized is the API entry points, they're really our controller. This is where we accept the request that's coming in. We have a payload. The payload is not what we give to the business logic. The payload contains the data that we want to pass on. So for example, for API gateway, the payload is an HTTP body, right? The headers and the body. We parse out the body into a JSON document. The JSON document is then converted into a C# class. We extract the properties from that, basically that request class we saw it earlier. It's only used for describing what the request looks like. And we pass it on now to the business logic to say, hey, can you do this on my behalf? The business logic operates on the data it's getting. It has an implementation of its dependencies for fetching other information or storing, making modifications. And again, it is completely decoupled from the controller. Now, you may have actually done this by accident. It's actually a fairly natural pattern. I mean, there's a couple of gotchas, and we'll talk about in a sec. But it's pretty straightforward, right? I mean, we're decoupling the business logic from our communication mechanism, and we're also decoupling our business logic from any kind of I/O operations, input and output, reads and writes. What makes Lambda kind of interesting is by nature, what Lambda is, it plays both the role of the controller and the dependency provider. So the way that our classes interact will actually look like this. Our controller gets the request and it initializes the business logic, but by basically giving itself as the implementation of the dependencies. So the business logic gets invoked by Lambda, right? The request comes in, it cracks open the request body, takes out the parameters once, calls the business logic. Business logic may now want to interact with the outside world, which calls back into the implementation of that interface inside the Lambda function. Since Lambda function to be single purpose, that lines out really, really nice. And really what helps for me as kind of like visualizing it, you can think of the Lambda function as almost like a membrane with the outside world. And inside you have your business logic, and it's just pure logic. It is unaware of any IO operations directly. And your Lambda code acts as the gateway, both for requests coming into your system, where it does the translation of the request format into your logic format. And similarly, when the logic wants to do something with the outside world, like store a record, it interacts then with the implementation that you want to use, because you're running inside the Lambda environment. If you were running inside a container or hosted your business logic somewhere else in a different environment, those implementations might be completely different, but the logic should not change. You're still trying to achieve the same business outcome. So there's a few things to keep in mind for when you write a dependency provider, and we'll cover those in the code in just a second. The key is you have to make sure that you capture all IO operations, all read writes that your code depends on. And that's where earlier I alluded to, Lambda makes it a little bit easier than other systems, because when we work in serverless on Lambda, where everything is ephemeral, we know that we have to interact with DynamoDB, or we have to maybe send a message to SNS, because the Lambda environment is not going to stick around. We can't keep state there. I mean, other than for caching, which is a entirely separate topic. So it is, generally speaking, fairly easy to identify what our dependencies are. Some of them, though, a little bit less than others. One of them, it's probably not the first one I always add, but it's the one that I always realize after a while, is time. If your business logic anywhere says, hey, give me the current timestamp, that's an outside dependency. It may not look like IO, but the reality is it's not something that you can actually, that is contained from within your business logic. You're asking the CPU clock to give you a timestamp. Similarly, if you're logging, if you're writing an error message or something else, you should really look at that as an outside world dependency. You're writing back to another system. And once you declare them, you can then validate that they are what they should be. If I control time of, when it gets read, then I can make sure that when I look at the outcome of my business logic, I can validate it has the timestamp that it should have had, or that the relationship between things, for example, the ordering of records is timestamp based if I want it. And that's, that's really what you're trying to aim at: perfect predictability. Everything, every side effect, every response value, you should have 100% control over what it is. And if you do, then you know that you've that you've been tracking all the read-write operations that your business logic might define on. A thing to avoid, which is very easy to fall into, is you don't want to pass in your dependency provider large interfaces like, oh, you need access to DynamoDB. No problem. Here is an Amazon DynamoDB client interface. Because when you write your test harness, you have no idea which methods the business logic might be invoking. Instead, you really want to right-size them. So you want to be as specific as possible in what you're trying to achieve. I'm trying to read this record. I'm trying to write this record. I'm trying to delete this record. I'm trying to list those records. Just enumerate out all the operations there, because in order to test them in a reliable, consistent way, you're going to have to implement them. And if you don't know which methods are being invoked, you either implement an entire DynamoDB abstraction, which don't do that, or you're building into your tests knowledge about the implementation when you shouldn't do that either. So instead, you want to keep the surface area, your dependencies, as tight as possible. Another gotcha, it's just easy to happen, is you have your business logic implementation where really everything should be, and then you have this other, the wrapper, that kind of allows you to marshal information back and forth. It's very easy to fall into the trap that you add inadvertently business logic in that marshalling code. Try to be cognizant of it, look out for it. A good way of seeing it is if you see that you're doing the same kind of logic in your Lambda as you do in your test implementation for your dependency provider. Odds are that shouldn't be the case. They should literally only be what is needed in order to get state from somewhere or put state somewhere. If you're doing any kind of manipulation of that information and it's the same in both, that should probably be in the business logic. So just look out for it. Excessively broad functionality, it's really hard then to implement those as dependencies. And then another easy gotcha is, you saw earlier, I threw an exception for like, there was a 500 error or not found error. Those should not be thrown by your business logic. Your business logic should not be aware of what the communication protocol is. It should not know, oh, I'm returning an HTTP error, like, status 404. That cannot be the case. Your business logic should then throw an exception like key not found, or something that however your business logic expresses itself, or try to do something and return a false, and then that's indication that something didn't work. You cannot have embedded. That's, once you have those, they're really hard to get rid of, and then they're a total code snap. Your business logic needs to be agnostic of the communication medium that is being used. Doesn't matter if your Lambda is implementing an SQS, a response to an SQS message, if it's an API gateway and so on. Your business logic just needs to get to the payload, do its thing, fetch and update information as appropriate, and return a response without knowing in what kind of world it's living in. If otherwise, you probably have the abstraction not quite lined up properly. So let's go back to the sample from before and just look at how it has changed now that we're introducing a dependency provider. So the first thing I want to do is, let's see. So I said that was example 2. So let me close these guys so I don't accidentally open something that is not correct, because that would be very confusing. So the module definition is identical to before. We haven't changed anything in our stack. We're using the same resources and so on. So that's all identical. We still have the API function project. There's a new one here called test, and we'll look at that in a second. But under API function, we now have 2 files. One new one here is logic CS. I tend to use very simple names. That can totally backfire, so it comes really down to your own practices. If you have multiple types of logic that are all in the same file or project, obviously give them a prefix like shopping cart logic. In this case, it was simple enough to just call logic. And this is where our business logic resides, and then our function invokes it. So I think it's a good spot to start off with looking at the logic itself. And it's going to look very familiar. For good reason. It's pretty simple, and again, almost trivial in this case. We're adding quite a bit of code craft to make it more testable. But in a real world scenario, your business logic file is considerably more complex than what I'm having here. So the dependencies identified by this particular implementation are, we need to be able to access the current time so that we can give a new blog post timestamp. We need to also create an ID for new blog post, GUID. And again, that is an outside dependency. If you want to be able to predict what the ID is going to be, you have to have control over it. And then the rest are fairly simple, straightforward methods that are going to map to almost identical calls from before. And those were very similar to the data access client methods that had the ability to create a post, to get a post by ID, to list what post exists, and then also a logging call for logging from inside the business logic when something happens and we want to report back. And the cool thing is this makes logging now testable as well, which is really, really valuable if you want to ensure that under certain error conditions, you have certain kinds of information being produced by your business logic so that you can help with troubleshooting later on. You can now validate that that is the case. Because the only way to interact with the outside world is by calling one of these methods. Everything else has to be fully self-contained and stateless effectively. The entire state is captured by, the entire world is captured by the parameters being passed in and by your dependency provider. So the initialization of the logic is equally simple. When we get initialized, we need our dependency provider. We check that it's not null, so we catch that early. We expose it through a private property. And then these, again, the implementation will be trivial because most of the complexity is abstracted out here. But we have a method to convert Markdown to HTML. That does exactly what we expected to do. We have our create post as before, that creates a new post, except now, every time we were dependent on something in the outside world, we say provider dot, and then call the appropriate method. So everything in here is now nicely abstracted away from what we might depend on from the outside world. And it all goes to a very narrowly defined interface. And that has some really nice properties, and you'll see those in a second. So again, I'm not going to repeat all of this because this code should look extremely familiar. It's almost identical to before, except instead of going to the concrete implementation data access client, like we had earlier, it now goes to an interface called provider. And again, the dependency provider interface is defined specifically for the needs of this business logic class. It's not going to get reused anywhere else. It has one purpose and one purpose only, and that is to track what this logic needs in order to operate successfully. And that's it. If you have another business logic, like it will have its own dependency interface and so on and so forth. Each one has to have their own. How they implement it and what they share, that's an implementation detail. But from a perspective of associating things, one interface, one business logic class, period. So now that we have that, when we go back to our function code, the changes here are rather trivial again. So we now have the logic class. We initialize it where we initialize our data access client. And because we are, I like to anthropomorphize, our Lambda function is an implementation of the dependency provider of the logic that it's going to invoke, we're going to use explicit implementation of that interface to provide all the outside world access that our logic needs in order to operate successfully. And so implementation of preview async instead of calling Markdown directly. Markdown is in the business logic. Lambda should have no idea which library you're using here. Use whatever you want that achieves the business objective. Instead, it's just calling logic. But again, the generation of the response is the responsibility of Lambda function. Lambda is responsible for cracking open the request and generating the response. The logic cannot be tied to these definitions because those are specific to your communication protocol. So keep that in mind. If you see that you're using your request model classes inside your business logic, you tainted it. You coupled things that shouldn't be coupled. And again, it looks very, very similar to before. We saw the exception here when we get back a null from create post async, and so on and so forth. So very straightforward transformation. And again, makes sense because we had very little business logic. I mean, a lot of the logic we actually had to do more with how do we respond to errors and things of that sort, and how do we crack open the request and generate the response. All of that is going to stay in your Lambda function, so that can't really be shoveled over to the business logic. However, where things do change in a nice fashion is if we look now at the test assembly. So I like to call my test assemblies, I prefix them with test dot, so they're also nicely grouped together, and then I give it the name of the complete namespace. So that's simply this, where the classes reside that I want to test. So if there's multiple namespaces, it's the greatest common denominator between them. Then I have organize it by folders. So we want to write tests for the class logic. So I create a subfolder called logic tests. And then I create one test class per method I want to test. So in this case, our logic class has a method called convert markdown to HTML. And the reason I like doing it this way is it removes a lot of cognitive complexity. We are here to do one thing and one thing only, and that is to ensure that convert markdown to HTML, we have good coverage for it. So we test all the scenarios that we care to test about. In this case, I'm only checking for valid markdown. But another one would be to probably pass in like null or just something that's maybe too big. All the edge cases you care to test. I found it to be really helpful if you don't cram everything that you can test in your logic class into a single test file. It gets so overwhelming that you can't focus on the things that you want to test. Instead, by creating a test file per method, and you can use the same name for the class, as the method you want to test, it makes it just cognitively a lot easier, at least for me. So I found that to be a very successful strategy. Again, here, because it's such a simple implementation, it seems a little overkill. But as soon as you have multiple scenarios you want to test, being able to kind of like filter it out like that has been very, very helpful. So we follow our usual pattern: arrange, act, assert. I use Fluent Assertions library, which I'm a big fan of. It's really nice way. You can say, should and then be and what you expect it to be. And it runs the test and tells you, the error reporting is really quite nice with Fluent Assertions. So I'm a big fan. Okay, so what I haven't shown here is this provider class, right? I mean, that's kind of key. And it's brought in by this base class init. So it's very common when you take this approach that all your classes are going to have the same setup, if you will, because you're going to need an implementation of the dependencies that is specific for your testing purposes, and odds is pretty high. It's going to be the same for every method. It's just what you validate on the interactions. So I captured that in the base class init, underscoring it simply to have it at the beginning of the file system, makes it easier to spot, gets out of the way instead of being lost somewhere in the middle. And the big part in here is this nested class test provider, which is implementation of the DependencyProvider for our business logic. And so now I'm just exposing all the capabilities in ways that they can be inspected more easily, or they can even be set. So UTC now is this default UTC now value, but the test could override it and set another value if they wanted to. Same thing for ID counter. Records are stored in this list, so they could be inspected and validated. And then very simple in-memory implementation for every dependency we needed. When we create a record, we simply add it to our list of records and so on. There's one caveat here. I'm not copying the data structure. And because this is pre.NET 5, it's not using the read-only records class definition. So technically, somebody could modify a record in memory. You shouldn't be doing that anyway, so your test shouldn't be doing it. It would be nicer though if the language would just not allow it, right? But as long as we're stuck in .NET Core 3.1 land, that's not an option. Okay, that caveat aside, it's pretty straightforward, right? I mean, finding a record is simply you loop over the array, first one that has this ID, you return or you return null. And so we now have effectively a complete implementation of everything our business logic can do with the outside world, things it might fetch, things it might have side effects on. Logging, I didn't do any testing for here, so logging is just implemented as a no-op, and that's that. So now the init class, again, just initializes the test provider, so it's available. The way XUnit works is every test method gets an instantiation of its class, so we don't have to worry about state contamination and so on. This will be created per test independently, so life is pretty good out of the gate. And then we simply test everything we wanted to test. So create valid record, great. So I initialize my logic, I give it the test provider. I simply call create post hello world async. And then I get the record back. And because we have full control over all outside dependencies, I know the value is going to be 1 because ID counter starts at 0, gets first incremented and then converted to string. That's how we generate the IDs in this particular case. I know what the test timestamp should be. It's the default value since I didn't override it. And of course, I know what the data should be that I'm getting back. Similarly, when I list all the posts, here in the arrange phase, I create 2. I then ask to list it with a limit of 10. And then I check that I got back only 2. And then they have the IDs. I expect them to, they're tuples. So I expect them to have these values. Okay, you have ID 1, have the same timestamp. You have ID 2, have the same timestamp. More sophisticated, I could have set like a specific timestamps to make sure that they get the timestamp at the time. And a test, for example, here that's kind of like clearly missing is if I were to create 5 records and I ask only for 3, that it should return only 3. And it should be the 3 most recent ones, most likely, right? So I can check that basically the way things are implemented are correct. And again, I have full control over it. And then view post async is the same, again, straightforward. But now we don't have great coverage here, but it is broken down in a fairly intuitive manner. It is fairly easy to work with, and we can test the wazoo out of our business logic, which is exactly where we want it to be. Finally, think I was here, but I didn't show the implementation of the dependency provider. So what I like to do in the Lambda function, so that's the class I went back to, is explicit implementation of the interface. And the reason is, odds are you're not going to get your code right the first day. I never do. So probably you're going to add and remove members to your interface over time. By making it explicit, so by using this notation, if you ever remove a method from your interface, if you had it defined here, compilation will break, because you will say like, no, you can't define this method here. If you do the implicit part, unfortunately, it can't tell the difference if this method was meant to be part of an interface that you're implementing or just a method that your class has, unless it's private, not called anywhere, and you use a tool that's smart enough to see it and it tells you like, hey, well, you have this. So by making them explicit, you get the benefit that in case there are any changes to the interface, anywhere where you implemented that interface, it will break, and that's guaranteed. So I highly recommend it. And here we're just doing super simple marshalling. So we're just calling data access. We're not even doing an await. We're returning the task directly. And here we're calling the built-in logger function that the dependency is modeled on. Keeps things simple. But as you can see, it's really, really trivial. Now we can use again our datetime offset UTC now. We can give back our GUIDs here. So because that's the implementation we want for our real code. And you have a full working system. And this is the version of the code I was running earlier is this one. It wasn't the simpler one. But yeah. So unfortunately, now, as you can tell, you get the benefit that, okay, so your business logic is now fully testable, it's predictable, you have full visibility in what it does. There's a couple of complications. That's one is capturing really the dependency that you need to capture, but the other one is also, you saw that the code became more complex. By virtue of introducing this abstraction between what you need and what actually gets done, you've enabled the testability, which is a plus, but it also came at additional complexity in definitions. Now, in this particular sample, that was more pronounced than it would be in real world scenarios, simply because it was a toy application. The business logic itself was really, really small. And so most of it was taken over by the wrappers, like converting the payloads or calling out to other libraries. When you actually use it in real world scenarios, that overhead is proportionally much, much smaller compared to the actual logic that you're trying to test. I think it's a great pattern for Lambda because you don't have to worry then about the more heavy integration testing. Having the test is, of course, just part of the story. You have to run them. So having a part of your CI/CD pipeline, making sure that tests get run. And so as soon as something gets committed, maybe that breaks one of them. Or if you have a code coverage tool, if your code coverage drops a certain percentage, you get highlighted. So you don't maybe accept these pull requests if they aren't meeting your quality requirements. Now, in today's presentation, I only talked about really unit testing. It was all about how can we write the logic in our Lambda function in such a way that we can make it nicely testable, we can get good coverage, we can stay organized, and we have a model that is simple enough that we can follow it and have high probability of success with it. However, obviously in more complex systems, you also want integration tests. So that's going to be a topic for future conversation because it's significantly more complex. If your stack has outside dependencies, so it depends maybe on an existing S3 bucket, an existing table, or something else it's interacting with, these are going to have to be provisioned. They're going to have to be created before your stack gets created so that they can be passed in. That's the dependency. You're going to have to track those, and then you're going to have to simulate, no, not really simulate, but you're going to have to maybe initialize those stores with test data so that when you interact with the Lambda function that depends on it, it sees it and it does the action, you can observe the side effects. And all of that will have latencies because you can just apply something and immediately check if it's there. So integration testing is significantly more complex. So whatever you can get out of unit testing, that is going to give you a lot of bang for the buck. They're cheap to run. They run relatively fast if you don't need to build again and again. Although I guess you would have to run it every time just to show that the test here. Yeah, maybe I should go into the test project. This is by far where you're going to get the biggest win. The integration tests, they will require a lot more effort and investment. They are more valuable because you will be testing if there is any kind of logic that exists inside the data access client that has to work against the DynamoDB instance, or if the wrapper has to do any kind of transformation of wrapping, unwrapping, and changing things again that is specific to the medium that you use. They're obviously not caught by the unit tests, right? Because they're not really part of the business logic. They're more like how you project records into your storage system and how you fetch them again. But they're important. So integration tests help there, and dependency provider doesn't really help you. So that's what I had for today. You can find the code that I walked through on our Lambda Sharp repository on GitHub, serverless pattern -testable Lambda. Documentation is lambdashop.net. And if you try things out and you have any questions, you can always reach me at Lambda Sharp. So other than that, that's all I have. So I'm happy to take any questions. Thanks.